I expect people might be trickling in after lunch. But in case you don't know me, I'm Alice DeVidia. I'm the NCAR co-chair of the Polar Climate Working Group. And then we have two external co-chairs right now. So one is Ed. Can you stand up, Ed? He's very tall, you'll see him regardless. So Ed is just coming on as the external co-chair. He's at the University of Washington. And then Hansi Singh, who gave one of the plenaries yesterday, is the other Polar Climate Working Group co-chair. She's rotating off pretty soon, and she may come in, but she's not in here right now. So I'm going to go ahead and have us get started. I just want to let you know, so each person has about 12 minutes to give their presentation and then a few minutes for and our first presenter is Ching, and she's going to talk to us about clouds and the Southern Ocean.
Thanks, Alice. It's great to be here to be the first talk today. So the talk today is about observation-oriented cloud condensation nuclei, CCN modification over the Southern Ocean using the CAM6. I'd like to acknowledge all my co-authors. So a quick introduction, why do I care about the Southern Ocean clouds? For those of you who tune the model to see the global radiation, you know how sensitive the Southern Ocean clouds can be. However, they are very poorly understood for the reason that we have a limited available observation in history. Thus, most of the model parameterization are North Hemisphere oriented. As an example, you can see the figure on the right. It shows the bias of surface incoming shortwave radiation between the mean of CMIP6 model and the counterpart from satellite project during the austral summer. A large area of red color here essentially is saying the overestimation of the surface incoming shortwave radiation. Given we have the fair amount of radiation at TOA, scientists would hypothesize that this overestimating of surface shortwave radiation might be related to the clouds not being reflective enough over the Southern Ocean. Therefore, we are talking about the simulated entire clouds being not bright enough. From the observation perspective, JMACE 2021 published this paper talking about this natural marine cloud brightening scenario over the austral summertime. It shows the seasonal cycle of cloud droplet number concentration ND along the marginalized ice zone. This is discussed to be related to the seasonal increases of cloud condensation nuclei CCN because of the biological activity. Then, how is the CCN modeled in the CAM6? So quick introduction. Essentially, it's about water vapor condensed on the aerosol. Aerosol are parameterized by type, sea salt, sulfate, secondary organic, primary organic matter, and then by size. Icon mode, accumulation mode, and coarse mode. Accumulation mode AC is the most potential candidate for the CCN. Given we have the reasonable amount of supersaturation here calculated by the balance between the adiabatic cooling and the condensation of water vapor. So given the amount of updraft, and then we calculate the critical radiative of the aerosol, any size larger than that critical radiates can be activated as a nuclei and then falling out to become cloud droplet. At this point, there would be a very fundamental question to ask. So are those Southern Ocean clouds aerosol limited or updraft limited? For those two GCMs, including the UK ESM, the University of Exeter scientists have this study in preparation for published to using those SILBI indexes to quantify the partial variance of the response that can be attributed to the model inputs. As we can see in the figure on the left, it shows most of the tropical area, it's the updraft velocity dominating the clouds here. However, over the Southern Ocean part, as you can see by the arrow, it is the accumulation mode number being the dominant factor in the story over the Southern Ocean. I published a paper in 2024 talking about the latitudinal change of number concentration of accumulation mode AC over the Southern Ocean. As you can see the figure on the right, from Australia to Antarctic, a polar world, we do see the increased amount of total AC in black and the decreased amount of large AC in red, increased amount of small AC in blue. Essentially, we capture this increased amount NCCN over the summer SSO, the South Southern Ocean, based on that the NCCN is more dominant by the number of small AC. So based on the conclusion we have from the observation, the counterparts of the conclusion can be seen or not in the model would be a good question. So Christina and I did this nudged simulation with schemes on the left and the collocation method on the right to check the Southern Ocean clouds over the Southern Ocean, North Southern Ocean, South and South Southern Ocean, and over different regions in different months. So Christina and I published a paper in 2025 talking about this similar figure on the right is the latitudinal change of the NCCN, so separated by size. Here we see, although the icon mode in green and the larger AC in red are fairly simulated, it is the total AC in black, particularly the small AC in blue, that are underestimated. We're evaluating what is causing the underestimation of CCN by the Antarctic coast, and the CCN spectrum on the left shows that most of the time over the NSO, it's the sea salt overestimation causing in this NSO over November, while over the SSO in summer, particularly in February, it is the small sulfate that are underestimated in the CAM6. Then you'll be curious about in nature and by modeling, how is the sulfate and sea salt simulated in the model? By nature, when the wind is blowing over the open water, the wave breaking happens, which is released the film droplets and jet droplets, which can release the sea spray also into the air, which contribute to the CCN and also the ice nucleating particles, INP. In this study, I reduced the sensitivity of sea salt emission flux from the 10-meter horizontal wind speed to its 3.4 to its 2.8, based on those publications using the very recent in situ observation in the summer of over the Southern Ocean. While for the sulfate, the things can be more complicated because of the involvement of chemistry, but long time in short, the DMS, dimethyl sulfide released from the open water, are transferred and oxidized into SO2 and eventually to sulfate, which can contribute to the potential sulfate CCN in the future. In this study, I did sensitivity test about double, triple, and times 10 of the DMS fluxes as a surface emission to see the sensitivity of the CCN. Okay, now we're going into the results of the study. What are the models show after turning down the sea salt emission scheme over the Southern Ocean? As you can see, I plotted the scatter plot of simulation on the Y and observation on the X, colored by the latitude. As you can see from the control run on the left and the wind up speed updated run on the right, the CCN over 44 and 50, between 44 and 55 are largely improved because it's more close to the diagonal line here, while those blue dots representing the CCN over south of 55 are not largely improved, potentially caused by this potential sulfate over this area. As a quite typical case for sea salt, in this early spring 2017, I plotted the time series of the base run of observation in orange, base run in blue, base run on the top, update of sulfate in the middle, update of sea salt in the bottom. It can be seen that from here and here, the overestimation of CCN are solved after we tuning down the sea salt. This is also confirmed by seeing the chemical composition, including the mass concentration and number concentration as a function of latitude. I plotted the base run on the left and the modification, including both turning up sulfate and turning down sea salt in the middle. As you can see, after this change, the chemical composition has largely been changed after the simulation, after the observation-oriented simulation, which on the right corresponds well with the 0.5% and 0.2% supercharge saturation. Similar case, however, this is based on the sulfate, which happened in the very deep summer. In 2018, from Mawson to Hobart, the model underestimated those peaks here, here, and here, which got further underestimated when we tuning down the sea salt. It has to be by doubling, tripling of the DMS when you see in the middle that the peaks are well captured by the model. So the DMS tripling method is largely improved the NCCN performance here. Again, I checked the chemical composition. As you can see, the updates really changed the chemical composition a lot by changing the aerosol type from chloride-based to sulfur-based. Take-home message here, for the reason that this field camping markets measurements of aerosol radiation and clouds over the Southern Ocean covers a longer time duration and a larger area, which provides a great data set to not only look at the sea salt scenario, but also the sulfate scenario in different time over different region. Both modifications improve the CCN over the Southern Ocean. And the take-home message of the two sensitivity tests would be sea salt emission power law can be regional dependent. This can also be related to the wave, except the wind speed over the open water. And then the low bias of NCCN in the summertime over the SSL can be related to the lack of sulfur. No matter what is the right sulfur in the real atmosphere that scientists talking about a lot in the bottom part of this slides, it has very different complicated chemical composition that scientists hypothesis to be the real sulfur in the atmosphere. The CAM6 is just lacking of the sources of the S here. However, I'm not gonna talk about so much complex of chemistry here. Instead, I would go through a different path, which is to look at how would this change between the ratio between sea salt and sulfate would be changed by a lifetime of accumulation mode error also, which is also influenced by the synoptic updraft and down descent because of the close by region of the storm track, and eventually looking at its influencing on the Southern Ocean clouds. I would like to acknowledge my collaborators, including NASA from PNNL, who is doing the similar type of job, but on E3SM. I'd like to acknowledge Jack Chen, who showed me his script when I first visited NCAR, also Simon and Chuda, one from ACOM, from rail, from telecommunication, and offer suggestions and feedbacks. Yun Qianzhu from NOAA CSL providing instructions on the simulation, and people including Jesse, Isla, Cecil, Brian, who always have an open door policy to me no matter when and no matter what question that I asked. Those are the institutions and funding agencies that is helpful for this research, including University of Oklahoma, NSF, NCAR, and DOE. I would stop here for any questions and comments. Thank you so much.
But okay, there we go. So thank you so much. We have time for a couple questions. Anyone here?
Nice talk, Ching. I'm not doing aerosol things, but I just want to understand what is the implication of the microphysical parameterization improvement in current CAM6 model from your research?
So currently, this research is not reaching as far as microphysical perspective on this influences on clouds. This is based on cloud condensation nuclei perspective, saying not considering the updraft or the dynamic factors influencing on the clouds. What if the background aerosol loading is different after changing from the base run to the update on both sea salt and sulfates? So I think the implication for microphysical perspective essentially is going to be, if we changed and improved the performance of NCCN, would that first of all change the ND in clouds, particularly the low clouds over the Southern Ocean when supercooled liquid water are regarded as a top first priority in this scenario? And then the second thing would be how would the lifetime be changed, because we also change the lifetime of CCN over this area. Being a very pristine region for Southern Ocean clouds, exactly the next step to go is to start thinking about the microphysics part from CCN to clouds, like aerosol clouds interaction. Yep.
All right, do we have any other questions? I guess I have a quick question. There were a lot of headlines this week about penguin poop being a source of CCN, and I assume that's probably through like ammonia and nitrates or something, but we have in more seriousness, we're probably not adding penguins to CESM anytime soon. Yeah. But I do think coupling the biogeochemistry, especially in the marine system and in sea ice, as a source to the atmosphere would be really beneficial. So thank you so much for this.
Thank you so much. I also mentioned this fully coupled potential of ocean and atmosphere and chemistry and also biology would be super helpful in this story.
Yeah.
Thanks, Alice.
Thank you. All right, so we're going to move on to our next speaker. We have Chloe, who is going to be talking to us about atmospheric responses to Antarctic sea ice.
Yeah. So thanks for having me. I'm Chloe. I'm a grad student at CSU, and I'm going to be talking about some work I've been doing with my advisor, Dave Thompson, and then also in collaboration with Ed Blanchard-Wigglesworth at the University of Washington, as Al said, talking about the local atmospheric response to especially some of this recent Antarctic sea ice loss. So I'm sure all of you are very aware of this time series, which is of Antarctic sea ice across the observational period, where prior to 2015, there was a slight positive trend, and then since then, in the last decade, there's been really rapid change and lots of variability. And there's been quite a lot of work done trying to understand the causes of this variability and the reasons behind this big shift in the behavior of Antarctic sea ice, but there's been less work done on trying to maybe understand the potential implications of this Antarctic sea ice loss. There's been a couple studies I'll highlight here. One from England et al. In 2018 that was a modeling study looking at this particular figure is looking at the response of the jet and zonal winds from Antarctic sea ice loss, and then a recent paper from Simon Josie in 2024 that was an observational study that was looking at, in this particular figure, the change in storminess from a decrease in sea ice loss in 2023. And so we were looking to kind of extend on this work, and in particular, look at maybe could we start to use some of this observationally constrained data to explore the impacts of Antarctic sea ice loss, but recognizing that there's obviously biases associated with said data, and so how does it compare to some modeled impacts as well. So for the observationally constrained data I'm going to use, so it's monthly data, monthly gridded data, sea ice data from the NSIDC, a bunch of atmospheric data from ERA 5, and some cloud fraction data from Ceres. All this data covers the period from 1979 until this past September. And then for the model data I'm going to use, so I'm using PMIP experiments, or PMIP style experiments with CESM2. So if you don't know, these are atmosphere-only time slice experiments. They all have 100 ensemble members. The experiments are run for 14 months. The first 2 months are discarded, so you end up with 12 months of data, and they're forced with the particular experiments I'm using is one's forced with present-day SSTs and a future Antarctic sea ice state, and ones with present-day SSTs with a pre-industrial Antarctic sea ice state. So basically, if you take the difference between those two experiments, you can isolate the impact of just a change in Antarctic sea ice state on the atmosphere. So this gives you a more direct kind of ability to see just the implications of Antarctic sea ice change or loss in this case. So for the observational results, so I'm using kind of this local regression methodology, which is simply a grid point by grid point regression analysis, where, for example, this map here is a regression of turbulent heat flux at each grid point onto sea ice loss at each grid point, which is just inverted sea ice. I just do it onto sea ice loss just because we're interested in what the change in turbulent heat flux in this case is based on a decrease in sea ice. So the way you do that is, for example, that little black box there is, for example, a grid point, and you take the turbulent heat flux at that grid point and regress it onto the standardized value of sea ice loss at that grid point. So the regression results, every single grid point is treated individually. So this allows you to kind of, you can look at each grid point treated individually, and so maybe it can build some confidence into your results, but it also allows you to kind of explore the regionality of these relationships and see how maybe different areas are affecting different aspects of the atmosphere differently. So for this case, you see that quite generally, there's an increase in turbulent heat flux due to sea ice loss. That's not particularly surprising. That's been shown before, and this is, of course, this is from data that's across the whole time period, across all months, but there is a notable seasonality associated with this particular relationship. So now I'm showing regression results, the same grid point by grid point regressions, but this time broken up by season. So each column is a different season. I've listed the months at the top, and then at the very top, this is sea ice concentration onto itself. This is just to kind of give you an idea of where the largest variability in sea ice is, just to kind of have maybe a picture in your mind of where the largest variability in sea ice is spatially. And then on the bottom is turbulent heat flux regressed onto sea ice at each particular grid point, this time broken up by season. So you can see this big seasonality where you're getting the largest response in the winter and the smallest in the summer. And you can understand the seasonality just by simply a temperature difference being between the ocean and the atmosphere being largest in the winter and smaller in the summer. Now the turbulent heat flux for the rest of this talk, I guess I'm going to focus primarily on just August, September, and October, and that's mainly just because otherwise you end up with a lot of panels and it's a lot of figures to look at, but I'm happy to show the other months if anyone's interested. So we can look at, beside turbulent heat flux, we can look at other atmospheric variables of interest. So in this case, we're looking at turbulent heat flux on the left, then 850 vertical velocity, precipitation, and then cloud fraction all the way on the right. And these are the same grid point by grid point regressions onto sea ice, loss of sea ice. And so you see that in addition to an increase in turbulent heat flux going from the ocean into the atmosphere, you also see areas where there's an increase in vertical velocity, an increase in precipitation, and an increase in cloud fraction. Now, all four of these kind of responding in this way is not particularly surprising. They should kind of respond similarly, because if you have an increase in turbulent heat flux, you'd expect maybe from that heating there'd be more vertical motion and more precipitation and cloud fraction as a result. However, I think there's some interesting regionalities, especially with Omega, where particularly East Antarctica and around the Antarctic Peninsula pop out as having a larger response than other regions, versus the variables like precipitation and cloud fraction have a more uniform response. And now, since these are only for one particular level, we wanted to look at, does this response actually extend higher into the atmosphere? And so these regressions are, so the panel on the left is Omega at 500 and 850, and then on the right, that panel is temperature response now at 500, 850, and 2-meter temperature. And so the main takeaway from this is that based on these local regressions, your response is not isolated to the low levels of the atmosphere near the surface, but you're actually getting a response in vertical velocity and temperature that actually extends higher up into the free troposphere, which maybe has potential implications for maybe larger scale circulation. And so this is just, so that was just the observational results based on this local regressions, but as I mentioned, we wanted to kind of look at how those compare to now the modeled simulations. And so again, we're using two experiments, one with a future Antarctic sea ice state, which is less sea ice, and one with a pre-industrial sea ice state, which is more sea ice, and we're taking the difference between those. And so this figure here is just simply the difference in sea ice between these two experiments, just to kind of show you again, you're having a reduction in sea ice in the future sea ice run, and that it's kind of similar areas of where you saw that large sea ice variability in the observational data. And so we can look at similar variables in the models. So now we look at the response, or the difference in turbulent heat flux, 850 vertical velocity, precipitation, and cloud fraction. And again, this is the difference between these two experiments, so I think that's important. Obviously, the observational data was a regression, so you can't quite compare these apples to apples, but I think you can start to qualitatively compare these results from what we're seeing with the observations, which is that given a decrease in sea ice in these PMIP-style experiments, you're getting an increase in turbulent heat flux, an increase in precipitation, and an increase in cloud fraction. The 850 Omega results are definitely a little messier and a little more, it's not as clean or not as similar to the regression analysis, which is interesting. And we can kind of start to compare these results with the observations a bit more by kind of saying, so for the observational results, the regressions were all per standard deviation of sea ice, which works out to about 20 to 25% decrease in sea ice. These PMIP experiments, the change in sea ice between the two simulations was about 35 to 40%. So if you kind of start to say generally, okay, given those two amounts of decrease in sea ice, what's roughly the amount of increase of turbulent heat flux, precipitation, and cloud fraction compared between these two results? And what kind of is what I want you to point your eye to is that there is an increase in the amount of turbulent heat flux increased in the PMIP results and precipitation and cloud fraction, but it's only a little bit of a change. And given that there is a more reduction in sea ice in the PMIP experiments, again, you can start to maybe see that there actually are kind of comparable results, which I think is quite interesting. And then finally, so again, we looked at different vertical levels in the observations, so it's worthwhile to obviously do this in the model results as well. This is quite a different picture than what we saw in the regression analysis. So this is temperature on the left at 500 and 850, and then Omega on the right at 500 and 850. And temperature, there's very little response at 500 versus there's quite a similar response at 850. Omega is, again, a little bit messier. There's definitely a little bit of a response, but it also dampens quite a bit as you move up to 500. And so I guess generally, if you think about, comparing these with the observational regression results, that the observational results show that there's more of an impact higher into the troposphere than these results from the model do. So this work is very much kind of still in progress, but some of these key points so far we've been thinking about is that I think based on this local regression analysis, we can use this observationally constrained data to try to start to explore these impacts. The results can be kind of qualitatively compared to this PMIP experiments, and I think they are actually relatively similar. And then a kind of very notable difference between the two results is that the results from the observations show impacts much higher into the atmosphere than you're getting from the PMIP experiments. So my contact information. Happy to take any questions. Thanks.
All right. Do we have any questions for Chloe?
Very nice talk. Learned a lot. So I just have a question about the asymmetry of your cloud fraction and precipitation response to the loss of Antarctic sea ice. It seems like to the eastern side of the Antarctica, the response is actually the strongest. Is that just because of the change in surface heat fluxes?
Are you talking about, sorry, the change
Yes.
in these results?
Yes.
Yeah. So it is interesting that there's notable areas, where you're getting a much larger response, and I think that is due to because if you look at the temperature profile of the PMIP results, that's where you're getting the most heating. So I do think that's why those two areas pop up, because you're getting the most temperature response in those areas that I think are resulting in more turbulent heat flux and more precipitation. But it is notable that those areas pop out more, or those areas pop out as kind of hot spots in these that maybe in the grid point by grid point regressions, it's a little bit of a more uniform response, which is interesting.
All right. Any other questions? No? All right. Thank you, Chloe. Before we transition, I just wanted to say that Hansi, our other co-chair, is in the room now. So will you stand up and wave to people real quick, Hansi? So Hansi's been serving since 2020, and she's going to rotate off in February, but we have the three of us for a couple months so that we can have some transition between things. But feel free to reach out to me, Hansi, or Ed if you have any questions or anything. So yeah, I just wanted to make sure that everyone saw her talk yesterday, so you might have already known who she was. All right, our next speaker is Molly, and she's going to talk to us a little bit more about constraining sea ice thickness with satellites.
Thanks, Alice. Hi, everyone. My name is Molly. I'm currently an NSF, currently an ASP postdoc here at NCAR. But I'm going to speak to you today about some work from my PhD at the University of Washington, and really quickly want to shout out that a lot of this work was guided and supported by my advisor, CC Bits, and then the folks at the Data Assimilation Research section here at NCAR. A lot of what I'm going to present today is a survey of results from a project at the end of my PhD, which was attempting to constrain sea ice thickness estimates globally using the SEIS sea ice model. I've left out a lot of the details, especially as they pertain to the data assimilation side of things. If that's interesting to you, please come find me afterwards and we can definitely chat about it. But for the sake of time, a lot of that stuff is not explicitly in here. So, motivationally, the source of this project really came from the fact that we have biases in our sea ice models relative to observations, which I hope is not news to anyone in this room. But our models are often really important sources of spatiotemporally complete information, particularly when it comes to things that are difficult to observe. So we want to be able to both accurately use those models and then also improve them. And I'm kind of illustrating one front-facing version of model bias in the sea ice model by showing you here on the right an ensemble mean from a 30-member size 6 set of simulations that's forced by a data atmosphere and has been tuned to a less melt scenario in terms of the kind of annual average sea ice thickness in that set of simulations. And then I'm comparing it on the left to a recent observational estimate of sea ice thickness over a similar time period that's been estimated from the Cryosat-2 radar altimetry observations. And you can see that not only does our model tend to kind of overestimate sea ice thickness in many parts of the Northern Hemisphere, it also exhibits a different spatial distribution of thickness than the observations would otherwise indicate. And if we turn and look at the Southern Hemisphere, these differences are kind of even more pronounced. I will note that this validation product that I'm using on the left is similar in the sense that it is based on Cryosat-2 radar altimetry observations, but it's, as far as I can tell, currently the only thing of its kind that does a kind of gridded monthly estimate of sea ice thickness in the Southern Hemisphere. And in that publication, they do note that they tend to kind of have thicker estimates of sea ice across most of the Antarctic compared to other observational products, and they can't really say why that is. Maybe it is that the ice is thicker, maybe it's an error with their methodology, but if we compare these two things, you can see that there's quite a bit of difference, such that in absentia of other kind of validation information, it's hard to place confidence in either one of these sources of information. And when we get to that point, one approach that you can take to kind of reconcile differences between models and your observational estimates, or try to understand why they are so different, is to assimilate the limited observations that you have into the model. And this has been done fairly commonly now, I would say, actually, in sea ice models, where the two most commonly assimilated types of observations are sea ice thickness and sea ice concentration. And those two things have pros and cons in terms of their utility for this application. For sea ice thickness, we do have some available observations, but if they are temporally available over long periods of time, they're often very spatially limited. So thinking like in situ buoy moorings, for example. Whereas if they're more spatially available, thinking from remote sensing, then they often have much shorter temporal range. This is a bit of a bummer, given that more idealized studies have illustrated that assimilating thickness observations does actually improve our estimates of the sea ice state, both in terms of thickness and concentration. And then on the other bucket, sea ice concentration observations have the good fortune to be part of a much longer, temporally high resolution and spatially continuous record. And they're available in forms that make it easier to work with. But studies have also demonstrated that while they do an okay job correcting model biases for sea ice concentration, particularly near the ice edge, they can have negative impacts on sea ice thickness estimates in models, particularly in perennially ice-covered regions of the Arctic. Our project wants to make a case that we should think about assimilating a third type of observation, which is sea ice freeboard, which, if you're not familiar, is a measurement of the height of the ice surface off the height of the sea surface. It's typically a little more readily available than sea ice thickness observations, and in fact, many of our remotely sensed thickness products are estimated from the freeboard products, from the same missions. And freeboard is available from recent satellite missions, including Cryosat-2, which targets the snow-ice interface using radar altimetry, and ICESat-2, which targets the snow and ice top of surface using laser altimetry. And our kind of main motivation for this is that it hasn't been commonly done yet, which is a bummer because the observations are typically more widely available than thickness observations, and they tend to have lower estimates of uncertainty, which becomes important in the data assimilation process itself. And in particular, if we think about the ICESat-2 freeboard observations, they are available at a really unprecedented density, though only from late 2018 onward. So this figure is illustrating the number of observations in millions for freeboard that are available from ICESat-2 for the Arctic in teal and the Antarctic in purple over the beginning of the ICESat-2 collection record from late 2018 through 2020. The solid lines represent the 30-day running mean, and the shading represents the total observational count. So you can see over this time period, on any given day, you're talking between 1 million to tens of millions of observations, depending on which hemisphere you're looking at. And this is actually, in fact, too many observations to assimilate directly into the model, given that at a nominal of 1 degree resolution, you're talking about a model grid cell seeing anywhere between hundreds to thousands of individual observations, which actually tends to pollute the data assimilation analysis. But we can still make use of the majority of this information by aggregating it onto the model grid, which allows us to represent freeboard in each grid cell as a distribution. And from that, we can extract a representative observational value and more accurately constrain various sources of observational uncertainty with that grid cell level observation, which winds up generating an along track gridded freeboard product or data set that we think is potentially quite useful from the perspective of trying to constrain a sea ice model. So in another world, this would be a video that would very gently expand and contract with the sea ice cover to show you where there are freeboard observations in each hemisphere. But for now, I hope this is enough to convince you that we get pretty good coverage from this kind of reduced product in both the northern hemisphere and the southern hemisphere. So with this product, we can start to think about taking it and assimilating it into the CES6 model. And we do that in an ensemble data assimilation framework using the data assimilation research testbed that's maintained at NCAR. And by doing so, we can start to think about answering questions particularly related to whether or not we're going to be successful in constraining our estimates of sea ice thickness when we use these observations in this manner. And when we do so, what does that tell us about our model? This presentation is really targeted at the first question, which is mostly that a lot of the results from the initial attempts to do this have teed up ways that we can think about the second question, but not really conclusively given us a lot to work with there. So we're mostly thinking about, does this work in terms of constraining sea ice thickness? So to do so, we're going to assimilate our product of daily along-track gridded freeboard estimates into an ensemble of CES6 simulations, and we're going to validate against a number of different products for both sea ice thickness and snow, which will become important later on. I'm going to note that what I show for validation products are monthly gridded estimates of sea ice thickness. It's difficult to validate daily data at a spatially comprehensive manner. If you're interested in that, there are some buoy comparisons I can show you later. But our first step is to compare the assimilation impact on the model's estimates of freeboard. So here I'm showing you the % mean absolute error reduction compared to an unconstrained model ensemble mean when we use a particular thickness validation product, or freeboard validation product, which is the ATL20 available from NASA. And what you should point out, or what you should focus on here, is that blue colors indicate that we're reducing the error in our model by assimilating these observations. Red colors indicate that we're increasing the error in our model by doing so. And you can see that in both hemispheres, we're doing a pretty good job in terms of reducing the error in our model's freeboard estimates, anywhere between 20 and 80%. So this is a somewhat trivial result. You assimilate, you constrain a model with freeboard observations, you should improve your model's estimate of that observational quantity, but it verifies that our assimilation is working in the way that we intend it to. That picture gets a little more complicated if we then move out of the observational space and think about how these observations have influenced the unobserved parts of our model, including sea ice thickness. So here I'm showing you the same metric, but this time I'm using a validation product of monthly sea ice thickness compared to the thickness estimates in our constrained model. And you can see a number of things that kind of immediately jump out. First of which, across most of the Arctic, we're doing a good job reducing error in thickness estimates compared to the validation, which is, again, the blue color. But if we look at the southern hemisphere, we generally appear to have an extremely low efficacy, so not much change in thickness as the result of assimilating these observations. And then in the northern hemisphere, we have this fun little dipole hanging out, in which we appear to improve model estimates kind of in one part of the Beaufort Gyre and degrade the model estimates of thickness in another part. Both of these things are really interesting for the sake of time, and because it's, I think, largely a validation product issue, we're not going to talk much about the southern hemisphere today. If that's interesting to you, again, please come find me afterwards. But we are going to focus on what might be going on in the northern hemisphere. And that, I'm going to argue, is largely due to the relationship between freeboard, ice thickness, and snow depths, and how they interact with kind of pre-existing model biases. So here, I'm showing you annual average sea ice thickness in the validation product on the left, our constrained model estimate in the middle, and the unconstrained model ensemble mean on the right. And I'm highlighting that region where we have the dipole in model improvement versus degradation. I'm going to use a little visual aid to block out the bottom 2/3 of this region, and we'll point out that here the validation and the constrained thicknesses look pretty similar, which makes sense that this is a region where we're improving our model estimates by assimilating freeboard observations. But if we look at the other side of this region, it's actually the validation and the unconstrained model that look most similar, largely due to the fact that the assimilation appears to have thinned ice in the constrained estimate in this region. Which is a kind of what the heck moment. Why would they do that, especially given that the validation data and the model already kind of agree in this region? And that, I think, has a lot to do with how we represent freeboard in our data assimilation framework and how that influences snow estimates in the model. So remember that we're assimilating ISAT2 freeboards, which target the top of the snow and ice surface. So snow depth is kind of implicit in these observations, and they're used to update snow depth as well as ice thickness in the model. So the validation product that we're using for snow depth is on the left, again in the annual mean. The constrained model estimate for snow depth is in the middle, and the unconstrained estimate's on the right. And we'll just note in general that the snow depth magnitude in regions where we have the most snow is larger than both the validation or the constrained model. And that's particularly true if we highlight again that region that we were interested in that had kind of unexpected model degradation. We can target this a little more specifically by looking at biases. So if we actually calculate the bias in snow depth and ice thickness compared to validation products, this is what we wind up finding. So on the left is the difference between the validation product and the constrained model estimates of snow depth, where you can see red colors indicate we're overestimating snow depth in our model estimates, and blue indicate that we're underestimating snow depth. And then on the right are two versions using two different validation products of that same calculation for ice thickness. And the main thing that I want to highlight here is that there's a really tight spatial overlap between where our constrained model is overestimating snow, it underestimates ice thickness. There are a couple potential reasons for this. I think the most prominent one is that the way we represent freeboard as a modeled quantity, calculating it from snow depth and ice thickness in the model, is a combination, like a weighted combination of snow depth and ice thickness, weighted by their relative densities, which we assume to be constant. That equation tends to more tightly relate snow depth to the freeboard value than ice thickness to the freeboard value. There's also a potential that the length scales of sea ice thickness in the model tend to kind of overly aggressively smooth the sea ice thickness analysis, especially because we have such a dense observational network, and we're allowing those observations to influence a lot of the Arctic when we assimilate them. So there are potentially multiple contributing factors, and I don't have a nice neat bow on this story to tell you exactly what's going on. But snow is a really important plot element in my mind, and I'm excited to maybe get to update the story with some simulations that are running now on the newly reinstated derecho. So more on that later. And with that, I think I'll wrap up and just generally give kind of a summary of the current status of this project, which is that we find that these freeboards tend to improve our estimates of freeboard, and then also across most of the Northern Hemisphere, snow depth and ice thickness, with some exceptions. Things I didn't show are that this also improves model estimates of total sea ice volume in the Northern Hemisphere, though it has a more complicated impact on sea ice cover. Secondarily, as currently represented, we're going to acknowledge that these freeboard observations may have some limitations, especially given the way we represent freeboard in the model, when constraining both ice and snow at the same time in the Northern Hemisphere. And we currently have an ongoing experiment that's looking at just updating thickness without updating snow to see if that's potentially more effective. The thing I didn't talk about at all, but which shouldn't be surprising to anyone, is that validation in the Southern Hemisphere is really hard, and it's going to require a little bit of extra legwork. If you're excited about this or you know of any products that I don't know about yet, please let me know. And then, oh, that should be a 3. That's fun. But then the other directions that we're thinking about investigating a little more deeply, in addition to this snow question, is how our assimilation configuration choices and the specific observational network of ISAT2 potentially influence this analysis. So with that, I'll stop. I'm assuming that I went over time a little bit, but I'm taking any questions.
All right. Thank you so much. I think we have time for one question. Anyone?
Just a detail, which thermodynamics are you using? The bits and Lipscomb or the new mushy layer? So K-therm 1 or 2?
I'm pretty sure it's the mushy layer.
Okay, because I'm wondering if there's just feedbacks in the data assimilation and then the thermodynamics that are really influencing the freeboard. Might be interesting to try the bits and Lipscomb.
Yeah, that's a great point, Dave, especially in the context of how things operate in the summer, where we tend to kind of drastically reduce sea ice more than we should. I'll take a look at that.
The only other thing I was going to say is I believe Sarah Cassini is working on a product in Antarctica. It might only be some seasons, okay. So but you might want to reach out to her as a possibility.
Great.
So,
thanks, Alice.
All right. So our next presenter is remote. Is Alec online? We're going to hear a little bit more about ISAT2.
Awesome. Oh, I'm sharing my screen, right? Or are you?
We were expecting you to share yours.
Yeah. Okay. You see that okay?
Yes.
You can hear me okay?
Yep.
All right. Great. Well, thank you very much for letting me give this talk remotely. I really appreciate it. Yeah, today I'm going to be talking about our efforts to constrain CI simulations with ISAT2 altimetry data. So a nice follow-on to Molly's presentation. We're kind of halfway through this project, funded by the NASA ISAT2 science team. Big shout out to my colleagues Chris and Maddie, who are working with me on this project. Chris especially has produced basically every plot I'll be showing today. So I'm going to be talking mostly about that project, and I've got a few slides at the end referencing a newer project we have starting up about sea ice melt as well. And I gave a similar talk with a lot more background at the winter meeting. So kind of similar to what Molly said, I'm going to be skipping over a lot of the kind of methodological details. Apologies, but I think it's justified, and hopefully there's a decent amount of people in the room that saw that earlier presentation. There we go. Yeah, so we're kind of inspired by trying to think, looking at maps like this of sea ice conditions and trying to think how we can better use the altimetry record to constrain CMIP6 results. The kind of traditional method to date has been to use passive microwave concentration data to assess sea ice output. Passive microwave CF concentrations are shown at the bottom for the Arctic on the left and the Southern Ocean on the right. That makes sense. It's a really nice data set. It's a 40+ year record of quasi-daily information. It's really nice to use. You can look at trends. You can look at variability. The problem with it is that it doesn't give us a huge amount of information within the pack ice. So if we look at the Arctic in winter, there's a lot of white. So we just have a lot of fully concentrated ice and not a huge amount of information. Above the concentration, we start to see information we can obtain from ISAT2. So as Molly said, what we measure with ISAT2 is freeboard, the extension of both sea ice and snow above sea level. Those freeboard results for the Arctic on the left in green, and then for the Southern Ocean on right. And then again, similarly, we can also derive quantity of sea ice thickness from that freeboard. We're a little bit more confident about doing that for the winter Arctic, where we have better information about snow loading. And so if you look at these maps, you just kind of eyeball them, you can just start to see a lot more information, spatial information within those maps, within the consolidated ice pack. And that's the kind of information we want to better leverage for assessing sea ice models. The big downside and the big caveat of doing this is we have a much, much shorter record. So we've got about 6 going on 7 years of ISAT2 data compared to the 40+ year record. So, you know, our hypothesis is that we're getting close to the point in which we can use altimetry to do kind of similar types of constraint. So the two key things we need to consider when we do this kind of work are observational uncertainty and internal variability. ISAT2 is really, really good at measuring freeboard. It's very, very good at doing it, and it's done it virtually uninterrupted since it launched in 2018. So the observational uncertainty of freeboard is low. When we start bringing in additional input assumptions regarding snow loading and ice density, that's when the uncertainty radically increases. Again, I'm not going to go into the details, but we kind of have this summary of our uncertainty estimates on the bottom right there, which is what we use in our plausibility assessments. The other thing we then need to consider is internal variability. And as I said, because we're dealing with this very short window, internal variability is going to be higher than the kind of longer term means we might be getting from the passive microwave data. Our kind of an example estimate of internal variability from CMIP6 for freeboard, and this is the September freeboard, is shown at the bottom left. And unfortunately, there is a kind of a decent amount of internal model variability. But this is kind of similar to what we see with actually the area and thickness results too. So we follow a similar approach to other studies of looking at this for the larger ensembles and taking a multi-model mean. So we put that together and we can produce these kind of plausibility scores that, again, previous studies have presented that we're building on. Again, skipping a bunch of the methodology, there's a bunch of stuff we have to do to actually think a little bit about density, kind of some of the topics that Dave was just mentioning with the thermodynamics, but for now, we're just going to ignore that and say we can kind of estimate freeboard from the derived outputs of thickness and snow depth. And we can produce plots like this. So this is a plausibility assessment. Here we're showing Arctic Ocean annual means for the ISAT2 period. So all of the total freeboards essentially that we've measured over the Arctic Ocean. The observations are shown by the red point and the vertical line. So it's about 27 centimeters on average if you're interested. Then all of the CMIP6 results are shown below that. So we have the CMIP6 model mean, multi-model mean, and then all the individual models below. Those horizontal lines represent that combined plausibility based on the observational uncertainty and internal variability. Again, for freeboard, the observational uncertainty contribution to this is small, but the internal variability contribution is high. That width is quite big, so that makes it hard to kind of decide whether some of these models are implausible, but you can see towards the lower end of this ranking a bunch of these models that are considered implausible at the kind of 2 or 3 sigma level. Then on the right there, I'm not going to explain that too much, but that's the mean absolute error at kind of a spatial scale. So that's where we start to integrate some of that regional information about freeboards. So we can see this doesn't increase monotonically. So we know that there's some kind of offsetting regional biases that we should consider if we want to be a bit more careful about this type of constraint analysis. Doing the same for the Southern Ocean, we see a kind of much different response, a kind of much worse response, if you will, for the models. So that CMIP6 into multi-model mean is now significantly lower than the observations, whereas for the Arctic, it was miraculously right on top of it. And so there's a lot more models that are considered implausible. And again, this was kind of expected from previous studies that have analyzed sea ice area. We're hoping to add a bit more information about, as I said, the freeboard and thickness using this approach. There's lots of different versions of this plot I could show, but instead we try to kind of summarize it all in this plausibility matrix. So we have this table, and now the x-axis is showing all those different metrics that we're looking at. So we only have thickness for the Arctic. And then the models, we have the CMIP6 multi-model mean at the top, and then below that, the models are all ranked based on their kind of mean plausibility across all of these metrics. I highlight the CSM2 ones because I'm at a CSM meeting, and luckily they're doing quite well. So good job, CSM. This is the CSM2 contribution to CMIP6, and then the CSM2 Wacom models. Yeah, and there's been talk about some of these kind of little scores, like the late summer low sea ice bias. You can kind of see by some of the reds that we're observing in those rows. So there's a bunch of extra work that we did to look at how we can use that constraint. Obviously, the next question is, do we use exclusion? Do we use a weighting to then kind of do something with that plausibility analysis? We looked a little bit at the seasonal cycle in sea ice volume, and then we looked at a little bit more in terms of the regional plausibility ideas as well. So if you do want to learn more about that, we do have a preprint at GMD that goes into much more detail. So that was kind of what we talked about at the winter meeting, a very, very quick version. What we've been doing since then over the last few months is trying to add in some more CSM models. So that's what I want to show you in the next slide or two. So now just showing the same kind of plausibility matrix, but we've added a bunch of extra CSM2 runs in red. So thanks to Dave and Alice for giving us some access to Duracho to be able to access some of those runs. I really appreciate it. So some interesting things we can see here, the CSM2 less melt run, which I think has already been mentioned today, where CSM2 was calibrated to perform better in some of these kind of sea ice assessments, is now at the top. So again, that was somewhat expected because they kind of cheated and calibrated parameters to do so. But this just gives further evidence that was a successful calibration, if you will. So good job. We have the CSM2 large ensemble below that too. That's again performing decently well, and I'm going to touch a little bit on the difference between that and the CSM2 CMIP6 runs in the following slides. And then we have the kind of CSM development runs that are being generated towards CSM3. So those responses are a little bit mixed, and I think that's going to be touched on more today. The kind of blues in the Southern Ocean are those kind of positive biases in sea ice area that we're seeing as well, but just for a very, very short window. But it's quite mixed. It's not necessarily bad across the board. So yeah, a lot more we can think about, and we have this framework set up to explore even more of these if you guys want to. So as I said, one of the interesting things is kind of the difference between the large ensemble and just the regular CMIP6 contribution. The CMIP6 one was only 3 members, whereas the large ensemble has 50. It's the same forcing, so we were kind of expecting similar behavior, but we do see some kind of differences in worse performance with the large ensemble. And we wanted to look into that a little bit more. So this is just kind of hot off the press analysis that we've done over the last couple of weeks. So thanks again to Chris for really getting this done in time for this meeting. So here what we're showing is the Arctic Ocean area on the left, thickness in the middle, and freeboard on the right, from the CSM2 CMIP6 contributions, the 3 members in red with the multi-model mean in bold, and then the large ensemble in black, for this kind of modern era altimetry period, we'll call it. So yeah, what you can see is, again, this is kind of a different demonstration of the high internal variability, which makes this kind of assessment quite challenging. Again, we try and kind of capture that in our plausibility assessments, but it's hard, especially when we don't have a bunch of very large ensembles. Struggling a little bit with that. It's interesting that the CSM2 CMIP6 runs in this ISAT2 era. The 3 members all show very high sea ice. Again, it seems to be just driven by internal variability, but that was interesting to note. So we've done a little bit of work of trying to explore that. Sorry if I'm kind of running out of time, but Chris has done some nice work to use bootstrapping, where we try and take 3-member samples from the CSM2 large ensemble to produce a similar looking 3-member mean. You produce histograms shown here. This is an example of where the kind of distributions that we obtain from the large ensemble are consistent with the CSM2 CMIP6 run. Then in some of the other metrics, like the Arctic Ocean sea ice area, they're not consistent. We see a significant difference between the CMIP6 contribution and CSM2 large ensembles. So yeah, we're still kind of thinking a little bit about why that might be. Maybe there's some model drift things, but maybe we're just not fully capturing internal variability. I think I'm running out of time. I just wanted to, have I got time for just 2 quick slides? Maybe?
Sure.
Sure.
You won't have time for questions.
Okay, just I want to highlight, we're looking at sea ice melt. There's a bunch of models that give us sea ice melt information, so that's cool. They all happen to use size 5.1.2, which is interesting. Quickly, this is what they look like. This is July, averaged over a few years. We include CSM2 large ensemble 2, and then we have observations from this Sentinel-3 melt pond product. We see some very large differences between the models and the observations, and we want to find out why. If you're interested, please get in touch. And then final shout out is that, yeah, I'm doing a lot of work on the side to try and improve the ISAT2 products too. So one of the problems with freeboard is we limit it to 50% concentration. I'm trying to extend that using some kind of fancy interpolation schemes that Will Gregory and others put together to increase that down to open water. Then I'm also working on an all-season thickness estimate from ISAT2, which is showing really good agreement with that Jack Landy's ISAT2 product that Molly just showed, and a bunch of validation data too. And that was just submitted to the Journal of Glaciology with Jack involved in that study. So yeah, lots going on. Excited to see what you all might think of it. Thanks a lot.
All right. Thank you, Alec.
10 seconds for questions. Perfect.
10 seconds. Yeah, Molly, you might want to get in touch with him about whatever products they have too. Also, Alec, you couldn't hear the reaction from the room about the CESM2 less melt, but there might be some words to be had.
Okay.
I think those will be a follow-up later.
Okay, cheating was the wrong word to use there. I'm sorry.
Yeah. But let's go ahead. Our next speaker, actually coincidentally, is Jen, and she is going to talk to us about when snow becomes rain.
Alec, are you still there?
I am, yeah. Good.
Yeah, so basically I just wanted to say, like, what we did for this ESM2 less melt simulations was go back to the pre-industrial control run and adjust some parameters within the observational uncertainty, because we knew that the model ice was too thin, and we knew we could adjust the albedo and that would have preferentially affect the Arctic, where we were seeing that bias even worse. But then I just want to say, like, the reason we're reacting to cheat is because we had no idea what was going to happen, right? You just run the simulations and see what it looks like at the time you get to the observations under the forcing. So it's really, it's a model development exercise, and we're all really proud that it came out #1.
Oh yeah. No, yeah, sorry, I was joking. I promise I was joking.
Okay,
I'm mostly impressed.
Okay, yeah, well, are you going to publish that? That's my question.
I'll put it on a website somewhere.
Okay, thank you so much, Alec. Okay, so we're going to shift gears and talk about some work looking at atmospheric processes. So where snow becomes rain in the atmosphere under warming. And this is work that was largely led by now Dr. Thompson Munson, who works at Travelers Insurance now, but the paper that was about this work over Greenland got published this spring, so I thought it might be kind of fun to share with all of you. And then I did make some slides at the end trying to look at these processes across all of the Arctic and CESM 2. Oh, there we go. So part 1 is this published paper. You can read it. It's in GRL, an observational constraint for future Greenland rain in a warmer atmosphere. Just GRL, you have the key points, and so I can kind of lean on those to efficiently communicate what we found, which is that the first one is just basically a methods one. Warming alone, applied to spaceborne radar observations, provides a useful constraint on future Greenland rain occurrence. The second are sort of the results. So we have rain could double with 2.3 degrees of near surface warming. So that's a lot more rain over Greenland. And projected 21st century warming makes rain possible at all elevations and in all months. So basically, we're looking at a rainier Greenland. We're starting to see evidence of that from the limited number of ground-based observations that are there. But this observational data set that we're working with is actually a satellite. It's a spaceborne radar that makes measurements over most of the ice sheet. So we can really start to constrain where and when we might start to see more rain. So yeah, here's the strategy. These spaceborne radar observations are from CloudSat. We build up local statistics over time to map and understand the sensitivity of going from snow to rain. And we're very conservative and simple in our analysis approach. We're detecting the precipitation by saying you have to have a radar reflectivity greater than 0 dBz. And we're only looking where CloudSat can make that measurement well, which is not right at the surface because there's strong ground clutter from the surface. So it's at about a kilometer above the ice sheet, which is kind of nice because it helps us differentiate from things like blowing snow. And these are big events. Like if you have a precipitation that's being detected a kilometer up, it's definitely precipitating. And then for the snow to rain threshold, this is kind of a fun atmospheric science fact, right? We always think about phase transitions as happening very abruptly as soon as you get over 0 degrees. And that's sort of true, but actually there's things like evaporative cooling. So anybody who lives here in Colorado probably knows if you're up in the mountains and driving back, you can sometimes see snow even though it's well above 0 degrees. And that's because there's some near surface evaporative cooling. Colorado's very dry. So we went pretty simple here. We used a threshold of 2 degrees Celsius to really try to make sure that if we're saying it's raining, it's definitely raining. So what we can do is just look and see, for one data granule, what this kind of looks like. We get these swaths of radar reflectivity, and we can make a kind of transect across the ice sheet whenever the satellite passed over Greenland, and then we can discriminate between rain and snow. So the present day observations are really consistent with rain being pretty rare, only along the coasts and during summer. So this is figure 1 from the paper, just showing, again, accumulated over 2006 to 2020, this map of where it's snowing and raining in A and B, and then the seasonal cycle of that. We can see exactly what this text said. Rain's pretty rare. midsummer, and along the margins are where we see it. And we can see, we have a lot of data that are going into this, so that's kind of cool. This satellite is no longer operating, but it was designed to last for 3 years, so it did pretty well. And so then once we have this distribution, it sort of serves as a foundation for assessing the potential for future rain increases. And here what we're just doing is we're just taking the observed distribution and saying, where would we change phase based on our simple thresholding? Now, this seems very simple. It is very simple. But just ask folks about modeling precipitation over Greenland. You can ask people here at this meeting, and you'll know why this is a very effective and useful thing to be thinking about. It's hard to model precipitation. Precipitation phase over Greenland has been something that CESM has struggled with. So what we do is just, really simple. We say, okay, if it warms by 1 degree, how much more rain do we get? How about if it warms by 10 degrees? So here's just the fraction of Greenland precipitation consistent with rain under these different warming levels. So in black at the bottom, that's our current day. And then as you move up, obviously more rain. So you can pull out a lot of statistics here, raining a lot more in the summer, but starting to get rain in all months when you get to 2.3 degrees of warming. And then we can make maps. So for example, the fraction of Greenland precipitation consistent with rain under different warming levels. So 2.3 degrees is actually where rain doubles. You can see rain is, still not occurring at the summit of Greenland, but, we're starting to get it along the margins. At 7.3 degrees Celsius of warming, 50% of the precipitation below 1,500 meters is rain. And with 10.7 degrees, rain is 50% of the precipitation. So we did look a little bit at how much warming happens in some of the projections over this next century. And the 2.3 amount of warming is something that occurs in almost all scenarios, under all emission scenarios, under all models. The 7.3 and 10.7 are not really within the scope for the next century. So I think, this is kind of a nice example of how you can start to pair maybe more complicated estimates of how much it's going to warm with these very simple kind of warming level-based estimates. So some more maps, just showing you as a function of the month of the year. Again, you're getting a lot more rain, during the summer and during these kind of shoulder seasons like September and May. That's when the warming really starts to create more rain in the central part of the ice sheet. So the 3 key points, I already said them, so I won't say them again here. You can check out the paper, but it's a nice, I think, example of how you can think about things like how much is it going to warm and how is that going to change precipitation phase without having to really even go through using a model at all. But obviously we have models, so it's kind of fun to use them and think about them and think about what to compare this to. So I started looking at this in CESM2. Before I go to that, though, I just want to advertise that even though CloudSat is no longer in space, EarthCare was launched about a year ago. This is a joint European-Japanese satellite, and it has a spaceborne radar and LiDAR on board, and is making measurements in the polar regions. And I think this is something for those who are polar scientists and interested in observations to constrain things like clouds or boreal fire cloud interactions or things like that. These are satellites that are up in space that would be very attractive tools to use, and so I think you should really keep an eye on these data and use them. Okay, so just briefly, I'll talk a little bit about this, looking at snow to rain in CESM2. I've been trying to take an event-based approach with this, again, so that I can try to use some of the kind of conservative and simple principles of atmospheric science to try to really understand where snow might turn into rain. And so the Large Ensemble Project, and in particular the 6-hourly MORE runs, and anyone who can tell me what MORE means can get a piece of candy from me later. Jonah, do you know? Mother of all runs? Yeah, right. So we can build up these local statistics, and that's kind of cool because looking at the monthly mean when you're looking at precip events is kind of insane. Precip is very intermittent. And if you want to understand the atmospheric structures associated with precipitation phase changes, looking at the monthly mean atmospheric precipitation structure is not the way to go. You need really high frequency information. So I'm being really conservative and simple and thinking about these things. Large precipitation events is what I'm interested in. I really want to see where we went from a large amount of snow to a large amount of rain. And again, being very conservative with some of the snow to rain thresholds. And here just comparing early 21st century with late 21st century and trying to think about where this transition is happening in the atmosphere and what are the processes that control it. So this is just the 275K contour in the bottom level of CESM2 during these large precipitation events. So you can see this contour from May through September when it's up in the high northern latitudes. Other months of the year it's further down, like in Colorado in October. So basically you can start to see, okay, where are we going from like a regime where we could have some snow to a regime where it's just basically all rain. And obviously that moves, as we get into summer, that transition moves towards the pole. And so then I added in dashed lines the late 21st century. So just seeing, this kind of encroachment into the Arctic Ocean of where we can start to have conditions where like the atmosphere is really not going to support the development of snow. It's really going to be rain. One thing I really noticed when I started looking at this was just how much this near-surface air temperature contour in the bottom level of the CESM model, CAM, how much it looked like the ocean and looked at, obviously the near-surface air temperature is very strongly controlled by the ocean underneath it, and the ocean, in this case, is probably a lot of ice-free conditions starting to warm up, but not getting too warm. But then I was thinking, it's like that's not always the case for what's controlling the phase of the precipitation in the atmosphere itself, right? So I thought, oh, this would be kind of fun to think about, like, what does it look like a kilometer above the surface? Like, how much is the ocean influencing that? And that's where, yeah, this is these same contours, but now looking about 1,200 meters above the ground surface in the atmosphere. And one thing that's really interesting to me, at least, is just how different these look. So, rain doesn't generate at the surface. Rain generates in the atmosphere in a cloud, probably at a kilometer up. And yet there's a lot of studies, if you read them, they're trying to figure out how snow is turning into rain by thinking about how the surface temperature is changing. And there's a lot of interesting, rich structure in the lower atmosphere about what that vertical profile of temperature looks like. And that's going to be really important for the phase of the precipitation that's actually hitting the surface. So I think that's really cool, and I'm planning on playing with this some more and thinking more about it. Obviously, I didn't do as much playing because derecho was down, but I got some plots of CESM2, and I think I can call it a win. So yeah, I think that's all I had for you all. Just this question about where snow becomes rain with atmospheric warming. I just really encourage you to not forget about the atmosphere, because the atmosphere is actually the place where that phase transition is going to happen. So thanks.
All right. We have anyone? All right. Thank you, Jen. If you have questions, you can come find her after. Our next speaker is online. We have Ash, and they're going to talk to us about how winds are impacting Arctic sea ice. Unfortunately, because of illness, they're not with us in present, but you can go ahead and share your screen when you're ready.
I'm all shared.
All right, we can hear you and see it. Go ahead when you're ready.
All right, awesome. Sorry I'm not able to be here in person today. Maybe tomorrow though. But today I'm going to talk about isolating the contribution of observed winds to recent Arctic warming and sea ice loss. I'd like to thank all of my co-authors and all of the people who have funded me on this project. And I'd also like to say this was recently submitted to the Environmental Research Climate Journal. It's not available yet, but hopefully when it makes through reviews, it will be. All right. So we all know that the Arctic is warming 4 times faster than the rest. And here we can see that the decadal global and Arctic temperature trends from this ensemble show a large 0.6 degree Kelvin decade spread amongst the ensemble members and spread in the Arctic amplification factor of 2. This ensemble does capture the observations, the observed Arctic warming and Arctic amplification factor, but knowing that this climate model has so much internal variability adds unreducible uncertainty to our predictions of Arctic climate. So we need to understand the internal variability of the Arctic climate system better. But from previous analyses, we do know that the observed winds are critical to reproducing the observed sea ice and temperature trends and internal variability. Driven from those results, previous studies also asked how much does the wind contribute to recent warming and sea ice loss using historical climate models forced with observed winds. But what our study wants to ask is how much warming and sea ice loss the observed winds alone can generate without anthropogenic forcing and in a pre-industrial climate instead. But one other fact we want to consider is the amount of influence the observed winds has is on the sea ice dependent on mean state sea ice thickness. For example, thicker sea ice has more mass and is more resistant to wind stress. Furthermore, if we apply warming to both slabs, the thinner sea ice slab is more affected than the thicker sea ice slab because it has more thermal inertia. So we want to add as a caveat, what is the influence of the observed winds alone on recent Arctic warming and sea ice loss as a function of mean state sea ice thickness? So set up for this experiment, I'm using wind nudging to nudge the model winds to, in this case, reanalysis winds. So I'm using CESM 1 version 2.1. I'm using a fully coupled version, because I want the sea ice to respond. And again, I'm using a pre-industrial climate because we don't want the anthropogenic forcing. And as for nudging, I nudge the horizontal wind components, U and V, with reanalysis every 6 hours from 1950 to 2023 over 60 to 90 north and above 850 kilopascals. So these are all the data sets that I used for observations. For OBS, I'm using Array5 for reanalysis for temperature and sea ice, GISTEMP for temperature anomalies, and then NSIDC sea ice index for the sea ice. And for the PI control, this is sort of our baseline pre-industrial control, and it's just a random sample of the CESM2 pre-industrial control. And then PI nudge is our pre-industrial sort of climate 3-member ensemble, where each ensemble member has its wind nudged according to the previously discussed methodology. PI nudge less melt is exactly like PI nudge, except it has modifications from KL 2022 to generate thicker mean state sea ice. And then PI nudge more melt is also like PI nudge, but it has modifications for mean state thinner sea ice. Now, PI control and OBS sort of the two ends of the spectrum, and we expect that our nudging experiments are going to fall somewhere between them. And additionally, for PI control, if a nudging experiment is sort of within our pre-industrial control, it means that the nudging experiment could have plausibly occurred within the pre-industrial control without forcing from the observed winds. This is just a quick overview of what the mean states look like, particularly looking at the sea ice. On the top, I've got the Arctic sea ice extent, and bottom volume. These are the seasonal cycles. So PI nudge, that's the mean state. It comes from PI control, which is, again, the standard CESM2 pre-industrial control state. PI nudge less melt is, again, from PI less melt, which is the blue line, and it has a larger sea ice extent, particularly in the late summer, and larger sea ice volume year-round. And then PI nudge more melt is from PI more melt in red and has a much smaller sea ice extent in the late summer, and again, a smaller sea ice volume year-round. As to state, PI more melt, sea ice extent and volume are close to modern day sea ice extent and volume. So to start, we looked at the annual Arctic temperature over 1980 to 2023, and for all of these results, we're only looking at this time frame. And for the rest of the line plots, OBS is going to be in black, balance of PI control is going to be in light blue, PI nudge will be in purple, and PI nudge less melt is going to be in blue. and PI nudge more melt is going to be in red. And the closer to the OBS, the nudging ensembles are, the stronger the influence of the winds, and the closer to the PI control baseline, the weaker the influence of the winds. So looking at the 3 ensemble members from PI nudge, we can see that they do not reproduce the observed warming. We can also see that although PI nudge less melt is cooler and PI nudge more melt is warmer, neither one of them are also reproducing the observed warming, and all nudging experiments explain about 20% of the interannual variability. So the observed winds have some influence over temperature variability, but not long-term trends, and changing the sea ice thickness has no effect on that result beyond changing the mean state. And then we looked at the Arctic temperature annual and monthly temperature trends. And again, none of the, these wind nudge experiments are reproducing the observed or monthly annual trend. Sort of all of these trends are within what we'd expect for a pre-industrial control. For example, all the nudged experiments are between like 0.11 to 0.14 Kelvin per decade annually, whereas compared to the observations, that's about 0.7. And all experiments reproduce similar trends regardless of mean state. The sea ice thickness is not affecting the contribution of the observed winds to temperature trends. However, all of the experiments reproduce the seasonal pattern of the observed warming trends, i.e. we get the strongest warming in the fall, spring and fall, and the weakest in the summer. Moreover, so in total, the experiments are explaining about 16 to 20% annually, and they explain the most warming in the spring, about 30-40% in April and May. We also looked at sea ice, looking at September sea ice in particular. Again, none of our wind nudge experiments reproduce the observed trend. They do explain about 12 to 8% of the interannual variability. And again, changing the sea ice thickness mean state is only, again, affecting the mean state. It's not affecting the trend. And then if we were to back out and look at sea ice extent trends more broadly, we can see that, again, the wind nudge experiments are not reproducing the magnitude of any of the observed monthly or annual trends. And in total, in September, the sea ice, the wind nudge experiments are explaining about 10 to 16% in September and like 1 to 8% in March. We are reproducing roughly the seasonal pattern of sea ice loss trends. So we're sort of explaining some of the seasonal variability, but again, we also note that the sea ice, all of the wind nudging experiments produce roughly the same trends. So our mean state is, again, not affecting the wind contribution. We also looked at local temperature and sea ice trends for each season. For running this plot, I'm going to outline the format here. So each column is a season. The row on the top is going to be the observations ERA 5. The bottom row is going to be PI nudge. So that is going to be the pattern correlation between PI nudge and the OBS and ERA 5. And any stippling would indicate that the trend is outside what we'd expect for a pre-industrial control. So if you look here, for the Arctic temperature trends for every season, you can see that PI nudge is not reproducing the magnitude or spatial extent of warming trends in any season. It does have roughly the same spatial pattern of trends as the observations, supported by some fairly high pattern correlations. I'd also like to note that PI nudge and the observations have their strongest warming trends in the same location, and this is true for every season. And I'd also like to note that there's no stippling on PI nudge for any season, meaning that all trends are what we would expect to see for a pre-industrial control. If I were to focus in, on DGF briefly here, we have this pattern of warm Arctic, cold Eurasia. We do see this pattern in observations, but some of the research is still divided on whether this is forced or internally driven. Given that our wind nudge experiment is reproducing this pattern, we suggest that this pattern is internally driven. And And I just like to quickly note here that, so on the top is PI nudge less melt, and the bottom is PI nudge more melt trends. Both PI nudge less melt and more melt are nearly identical to PI nudge, so both increasing or decreasing the sea ice thickness doesn't matter. It's not having any effect on the wind contribution to temperature trends. And lastly, here's the Arctic sea ice trends for every season. Again, PI nudge is not reproducing the magnitude and spatial extent of the sea ice trends in any season. PI nudge does have approximately the same spatial pattern of trends as the observations, but it's generally performing worse for sea ice than for temperature. And PI nudge and observations do have their strongest sea ice loss trends in the same location for at least JJA, SON, and DJF, but not for March, April, May, because you can see in the Barents Sea, we have a lot of sea ice loss in the observations, but almost nothing in PI nudge. Some additional sort of discrepancies include the Sea of Okhotsk for March, April, May, and the Bering Sea for both March, April, May, and DJF. We do see some stippling, but for all the trends, it's about smaller than 2% per decade, so we can sort of disregard that significance. Again, I have here's the PI nudge less melt is on the top row and PI nudge more melt on the bottom row. Again, very, very similar results to PI nudge for the sea ice trends. So again, no effect on sea ice trends from changing the sea ice thickness. So in conclusion, the observed winds fail to reproduce the magnitude of recent Arctic warming and sea ice loss. They can partially reproduce the interannual, seasonal, and spatial variability of Arctic temperature and sea ice. So in short, like observed winds drive some of the Arctic variability, but not long-term trends. And our results are independent of mean state sea ice thickness. I do want to mention that we had to diagnose and remove wind nudging induced model drift. If anyone wants to learn more about that, I'd be happy to chat about it. Thanks for listening, and I'll take any questions.
Thank you, Ash. We have time for a question or two. All right. We don't have any questions in the room. I thank you so much, Ash, and hopefully you can rest your voice, and maybe we'll see you tomorrow.
Great.
Our next speaker is Ling Wei, and she's going to talk to us about microplastics and sea ice.
Thank you very much. I'm Ling Wei from CU Boulder. And today, I'm really excited to get to share more about work I have done simulating microplastics in the Arctic using CESM2. So before I continue, I would like to take a moment to thank my mentor, Alex, and our collaborator, David Bailey, for their valuable input and support. So we may hear a lot about microplastics lately and how pervasive they are in our daily lives. This leads us to wonder what actually happened to plastic after we threw it away. It never really disappears. It just gets smaller and smaller until it becomes invisible to our naked eyes. So we call these small fragments as microplastics. By definition, microplastics are just small plastic particles with mean diameter smaller than 5 millimeter. And because of rapid increase in plastic use over the past decades and the mismanagement of waste, microplastics are now prevalent in the global environment and are a massive marine problem in the global oceans. And aside from the obvious pollution, the integration of microplastics poses questions about their effect on our Earth's climate system and health risk to consumers across food webs. And one of the interesting questions is if there are any microplastics in the Arctic.
Unfortunately, because although the Arctic is far away from the direct source of anthropogenic pollution, recent studies have shown that microplastics can be found almost everywhere in the Arctic. The rivers, oceans, glaciers, sea ice. So the microplastics were first discovered about roughly 10 years ago in the Arctic in 4 ice cores retrieved from different locations in the Arctic Ocean. And in this initial study, a total of 6 synthetic polymers were reported, and its concentrations were estimated. Surprisingly, the concentrations of microplastics are really high, and it's even higher in the Arctic sea ice than the underlying ocean. So this high concentration in the sea ice later has been confirmed using more samples collected at different locations and in different years. So here, this schematic plot summarizes the typical range of microplastics in the Arctic sea ice and ocean, and we could see that the concentrations of microplastics are about 1 to 6 order of magnitude higher in the sea ice than in the underlying ocean. So that means the microplastics have accumulated far from population centers, and Arctic sea ice is an important sink and means of transport for microplastics. But how do they get there? We do not know. Well, the reasons for its high concentrations in the Arctic sea ice are still a mystery, and with this high concentration, the distributions of microplastics in the sea ice and ocean are still underreported. And additionally, a few modeling studies even have focused on the Arctic marine microplastic problem and explored how big the impact of Arctic microplastic in sea ice on global oceans. That being said, how the ice growth and melt processes affect microplastics in sea ice and ocean are largely unknown. So to better understand mechanisms and factors concentrating microplastics in the sea ice, we have been working to implement microplastics as a new class of passage tracers in the CSM2. So far, we have added 2 tracers. One is neutrally buoyant and one is positively buoyant microplastics. Both tracers are added in the sea ice and ocean component of CSM2 plus the coupler, and we applied a constant rising velocity to the positively buoyant microplastics, so buoyancy only affects the tracer movement in the ocean. And we are not modeling the negative buoyant microplastics in the model because it is just that the negative buoyant microplastics will not reach to the Arctic Ocean where they will interact with the sea ice. Well, because we would also like to know how microplastics get trapped in the sea ice and released from the sea ice. There is ice melt processes. Fundamentally, we need to know how to parameterize them in the model. There are 3 factors that we could really play around. The optic factors for the congelation ice and fragile ice growth, and the release factor for microplastic, there is top ice melt process. Currently, the observations have typical no knowledge of ice history to really understand how observed concentrations relate to these parameters. So to address this, we are collaborating with the lab team from University of Washington who grow ice artificially in the tank with microplastics to investigate these parameters. So we will decide on these final parameters in the near future based on our sensitivity tests and lab results. But here we just assume the same amount of microplastic concentrations in the sea ice as in the ocean. There is an optic factor for the optic factors. So once the model is set up, we have run 3 1-degree sea ice ocean coupled simulations with microplastics. The first simulation only includes optic factors where microplastic will be trapped into the sea ice during the ice growth process. And the second one does not have neither optic nor release factor. And the third one, the third simulation includes both optic and release factors, where microplastic will get trapped into the sea ice and released from the sea ice. So the model the model is forced by a global microplastic forcing field, which prescribes the mismanagement plastic waste input along the coastal lines in proportion to the total population along the coastal line. So we scale down the total plastic input for neutrally buoyant microplastics and positively buoyant microplastic by a factor based on the global demand for each type. So 19% for neutrally buoyant microplastic and 49% for the positively microplastics. After running for 60 years, we now compare to the ocean surface total microplastics of simulation 1 and observations. And it shows good agreement with observations and can change some key features in the model. For example, the Pacific garbage patch. And then we wonder how ocean microplastics change globally by having microplastics in the sea ice. And here I'm showing the difference maps between the cases with and without optic factors. The top panel is showing the top layer difference maps, and the bottom is showing the vertical integral of microplastics for neutrally buoyant and positively buoyant microplastics. Both figures show less microplastics in the Arctic region and more microplastics in the North Pacific and North Pacific jars. Although the changes in the North Pacific is quite small, about 1% of total plastic change. But that indicates that means that the optic factors could really reduce microplastics in the Arctic Ocean and increase microplastics in the North Atlantic and North Pacific regions. Now let's switch gear and see what happens in the Arctic. Here I'm showing the ocean surface microplastic concentrations and microplastic concentration in the ice in year 60 of simulation 1. And we can see two things. The first, there are some differences in the spatial maps for neutrally buoyant and positively buoyant microplastics in the Arctic Ocean. And secondly, the model can really reproduce higher microplastics concentrations in the sea ice than in the ocean, which is quite consistent with observations. But note that this simulation only includes optic factors trapping microplastics into sea ice during ice growth. And we want to know if there are any effect for the release factor. So simulation 3, which includes both optic and release factors, where microplastic will be taken into sea ice during ice growth and released from sea ice during the ice melt. So here, let's start with neutrally buoyant microplastic first. So here I'm showing the comparison between the cases without and with release factor. And the left panel is showing the concentration in the ocean, and left panel is showing the concentration in the ice. And well, we can see the ocean concentrations of microplastic in both cases are very similar, so meaning that there are very small differences between these two cases. And also we can see we still have much higher concentrations in the sea ice than the underlying oceans. So this is also true for the positively buoyant microplastics. So to summarize, the model can really reproduce higher microplastic concentrations in the sea ice than in the ocean, which is consistent with observations. And the model shows differences in spatial patterns for neutrally buoyant and positively buoyant microplastics. And the upticks of microplastics in the sea ice does affect Arctic and North Atlantic microplastic concentrations. And as for next step, I would continue to work exploring how microplastics are exchanged between sea ice and ocean, and assess the role that sea ice plays for changing the Arctic microplastic distributions. And if possible, I would further investigate how future climate will change the impact of microplastic distributions in the Arctic. So I will stop here, and I'm happy to take any questions. Thank you very much.
Thank you, Ling Wei. Do we have any questions?
So could you go back to page 10, please? Yes. Could you give some more explain about why there are regions of the microplastics increasing? I understand that if the sea ice uptakes the plastics, it reduces, but I don't understand why it increases.
Well, to be honest, I do not know either. Well, because, and also, I will take into deeper depths about why it increased in the North Atlantic and North Pacific if we don't really have uptick factors in the model. But so far, I don't really have a confirmed clear answer to you, like why we have really increased in the North Atlantic. But that's really a nice question, and I'm looking forward to it. Yeah.
Are there any other questions in the room? All right, I had a question real quick. If you go forward, I think 2, other way. No, go towards the end of the presentation. Keep going, and go forward one more. So go back. All right, for this one, I thought it was interesting for the sea ice, the positively buoyant microplastics.
Yeah.
On the far right in the sea ice, it looks like there is a big difference if you have the release, whereas you said with the neutrally buoyant it wasn't.
Yeah.
Do you have any idea why those?
So for the release factor, we set is as 0.03, which is same as the black carbon because they are both hydrophobic. But I don't really have chance to why it reduced this much in the sea ice. But also I'm showing the annual mean, so I need to look more about seasonal changes in the microplastics in the sea ice. So sorry, I don't really have clear answer to you as well.
That's all right. Thank you so much. All right. So our last but not least presenter is Dave, and he's going to talk to us a little bit more about CESM 3 and where it is right now.
So I'm also going to go through some of where we're at with the physics as well, because some of you weren't at the winter meeting. So Dave Lawrence had highlighted, some of the processes and things and biases and things like that, and I'm going to go into a little bit more depth about some of these biases that we have in the model. But main thing I wanted to go over first was the sort of timeline that we were looking at last year. So you can see here the timing of the winter working group last year in February, and then the summer meeting last year. We had this ambitious timeline of getting all this physics in that we really wanted in the sea ice. But things change, deadlines shift, and so this is now this year's plan. You can see here I've changed the x-axis, so we're here now, summer 2025. We've done pretty well. We've gotten 3 of these major parameterizations into the model and running in all of our standard coupled simulations. Although the advanced snow physics, we didn't bring in all the aspects of this. I'd be happy to go over it with some of you. So the pond improvements, the advanced snow physics, and then this new congelation formulation. But The thing we're still a little bit struggling with is the flow size distribution wave interaction part. I mean, the code's there. We're just trying to decide some sort of aspects of it that we want to try to overcome before we sort of officially start running with it. All of these other things have been moved probably, again, several times. They keep shifting right on this timeline, and, they're going to be hopefully in future versions. And then another key thing about this is that for the CSM3, we've also developed this new diagnostic package, CUPID. So the acronym is CSM, Unified Post-Processing and Diagnostics. And then as a part of this, I have a new CI's key metrics notebook with a lot of new diagnostic plots and things like that. One of the key additions is that we've added the CSM1 large ensemble and the CSM2 large ensemble onto a lot of the plots. So that helps us put things into perspective with the two previous large ensembles and sort of how we're performing in terms of those. We have several spatial plots, to compare two runs and things like that. And I'll use some of that in the coming slides. And then another thing that's come up, which is kind of a side rabbit hole thing, is that we're looking at the observational products and bringing them into the diagnostic package. And Dave Schneider's in the room here too. So he's done a lot of this too previously. But what you can see here is the dashed lines are extent, and they agree pretty well generally between all of the different products. So there's the NSIDC official area that you get, and extent. There's this newer climate data record developed by NOAA and NASA. And then there's this European product, the OCSAF, and don't ask me what that acronym is. But anyway, but you can see here that, again, the extent generally is similar in both hemispheres at the sort of min and max periods and so forth. But with the area, they're significantly different. And there's really big differences in terms of how the area is determined in the interior of the pack. And in fact, to the point that it seems like some of these trends might be slightly different too. So it has raised some concerns about what we should be comparing to exactly. I think we've kind of decided that the upper end of this is this NOAA CDR product, and that's probably what we're going to be using as our benchmark from now on. So Dave mentioned the Labrador Sea keeps freezing over. I thought it was worth going into some of the things leading up to this. This is a coupled model problem. And so I wanted to sort of take you through that, what's going on. So we have a high latitude precipitation bias. And we know this, in almost all of our runs, we're just getting too much precipitation, especially over Greenland, but over some of the ice sheet areas in the Canadian Arctic as well. So this leads to enhanced runoff. This is me running off. Anyway, but nonetheless, we get enhanced runoff from Greenland, and then that is we have this funny thing where we fan out both the ice and the liquid runoff using this mapping like this, and we're actually kind of fanning it out a little bit too far over the central lab sea. So we're getting too much fresh water pushed out over the lab sea. And then this is my little approximation of the horizontal mixing scheme. But basically, there's a lot of excessive horizontal mixing going on here too. So you're mixing in fresh water from the boundaries of the Labrador Sea, and you're bringing, again, too much fresh water into the central lab sea. Throw in a little bit of chaos. And so basically, the fact is that, these conditions lead up to a lot of fresh water, cold water in the central lab sea, but it's not necessarily enough by itself to guarantee that it's going to freeze over. Sometimes, we'll start 3 equivalent runs and all we'll do is just make a small perturbation and one of them won't freeze over and the other ones will. So it's a really challenging thing to really get at. But then, this is kind of low resolution. but it gives you the idea that when it goes, it really goes, and it impacts the meridional overturning circulation, and it just really changes the state of the model. And it's almost impossible to come back from this state. So even if you run out 100 more years, you can't really come back from it. So what have we done to maybe try to alleviate that? We've sort of gone to each of these sources. So reduce the precipitation somehow by changing the latent heat flux over the ocean, maybe making topographic changes to reduce the precipitation over Greenland in particular, reducing the flux locally using sort of artificial methods like restoring or just, reduction factors or something like that. And then also changing lateral and vertical mixing parameterization, sometimes locally in the LabC, sometimes globally. So those are the routes that we're taking, and there's been some promising results with some of these. The other interesting thing, back to the sort of OBS and then sort of model, is that we noticed that the Antarctic sea ice extent has been expanding very much. And when you looked at the seasonal cycle and sort of, in sort of a CSM2-ish configuration, the seasonal cycle was actually really good and it compared very well to the OBS. But what you'll notice here is that there's this interesting pattern of the sea ice being too high compared to OBS at the ice edge, like around 90 and minus 90, and yet it's too low here at 0 and 180. And so it's like somebody just grabbed it by the sides and pulled on it, and suddenly you actually get about the right overall seasonality, but there's still significant regional biases. And then somewhere in the development of the MOM simulation and the vertical coordinate, we noticed this got a little worse here. And then when we changed to the vertical HICOM coordinate in the most recent simulations, now you'll see the bias is just high all the way around. So we have a really high Antarctic sea ice bias. So that's a spatial picture. This is just to give you this idea of what I said earlier, that the two techniques for retrieving the ice area can still give you very significant pictures of, or picture differences of the ice area interior in the pack. So I'm kind of getting there. So anyway, so here's the seasonal cycle that I was talking about, and this blue curve here is one of the control runs that we have from pretty recently, and you can see it significantly overestimates the area in the winter months in the southern hemisphere. And then here's the two observed products that I talked about, the CDR and then NSIDC. Interestingly, CSM1 looks really good compared to CDR. CSM2 looks really good compared to the NSIDC, so you can pick whichever one you want. But one of the sensitivity runs, well, we did several. We did a nudge wind run. Ash talked about this. It does help a little bit. It moves the wind stress maximum a little bit towards the pole, but it doesn't really resolve the overall extent that well. But what's very interesting is this new run where we use the GFDL PBL. You see that it's not only much closer to the old runs, it actually is getting the seasonality better too. So it's really surprising. Now, is this a candidate for CSM3? We don't really know at this point. We're continuing things. We still have the wave interaction runs. We hope to maybe get that in. It does also decrease the ice extent somewhat, but it's not really going to fix the overall thing. And then a very hot off the press thing this morning that I did just from derecho coming back up. You can see here that I did this run where I changed the mesoscale mixing parameterization, the Gent-McWilliams, slightly. And you can see it does reduce the overall sea ice extent in the southern hemisphere a lot. Doesn't quite change the seasonality like we would like. But anyway, these are all potential candidates. And I got a minute left, but this is just basically summarizing everything I've said. But I think the important thing to think here is we keep harping on the CSM administration to say, you know, the southern hemisphere is important and we don't want to live with this bias. So with that, I'll take questions.
right. Thank you, Dave. So yeah, if you were here in the winter working group meeting, you might think you're still having the same problems, but we really have been looking into it and trying to understand it. So are there any questions for Dave or even me or the other co-chairs or anything like that? I'm going to start with Alex.
Yeah, thanks, Dave. When did you look at the rest of the Arctic? So outside the lab C, how does the sea ice look beside the lab C, like thickness-wise?
Yeah, I didn't really show the results here. It just varies between the runs, but overall, our overall Arctic bias is pretty good in general. It looks pretty reasonable. So, but that's another thing we still have to worry about is we could still potentially have to tune the Arctic sea ice a little bit. So, but yeah, right now we're focused on Lab C and Southern Ocean. So, yeah.
Yeah, thank you for the presentation. So, regarding this Labrador Sea, so we know that over Greenland, over the Canadian Arctic, there is a snow cap. So whatever, when you get 10 meters, then you're gonna just send all like frozen runoff. Have you tried, if your snowpack is uninitialized, the moment it's building, it still freezes over?
Yeah, we did. I didn't mention those experiments, but basically all it does is just delay it, you know, because it takes a while. It finally builds up to the 10 meters, and then you start dumping the ice runoff and the snow or the liquid runoff in, and it freezes over. So we had one run, went 240 years, and then the Lab C froze over. So, yeah. Exactly. Yeah. Yeah. Ed?
Great talk, Dave. This is maybe more of a comment or like a PSA, but if you go back, I think, to your slides where you're showing all the sea ice area extent time series, where you were validating from the observation estimates. And I bring this up because it came up in actually a review I made very recently. If you look at the NSIDC area in the top left there, or in the top right? Like if you look at the red time series, the first decade or two, it looks like it's increasing. And the issue, I'm fairly sure, is that they have different sized pole holes.
Yes.
And the NSIDC website, they just give you the raw number, and you have to kind of dig in to see, oh, there's just a bigger pole hole. So you're actually summing over a smaller kind of mask early on, and it's basically an artifact. Yeah. And I think OSISAF just assumes that the pole hole's covered in sea ice.
Yeah,
right?
Absolutely. And and that's why generally NSIDC sort of sticks to extent, because they do fill in the pole hole with extent, but they do not for area. And so, yeah, you're right. There are some weird artifacts there, but, you know.
Not for the NSIDC area time series.
I know that index doesn't, but at least when I plot it, I fill in the pole hole.
Right.
The time variant.
Right.
But I just want to point out, because if you just...
This is the official NSIDC index.
But you're not filling the pole hole.
I am not.
Yeah, and that's the issue, that if you go on the NSIDC website and you just download the sea ice area index, this is it.
Yeah.
And you have to, like, I mean, and this happened, I was reviewing a paper and this came up, and
But even if you fill the pole hole,
then it matches the others,
no, it
doesn't it?
still is quite different.
Yeah.
But in terms of the mean state, I think, but in terms of the trends, it matches the others a lot better.
Yeah. I mean, it's right. Yeah. Right. So maybe it's a rabbit pole hole, but nonetheless, it's just worth highlighting these big differences and sort of what our truth is. That's all I was trying to say. So, yeah.
Okay. Maybe the big takeaway is that when you're using these observations, be really careful and read the documentation about what you're actually using.
Yeah.
Because there are some gotchas in there, and we've run into them in this. Are there any other questions, comments? All right, well, I think we're almost done. I want to make one announcement, which is if you're on the Polar Climate Working Group email list, Ed and Hansi and I will probably be emailing you about using resources. If you have a resource allocation, if you don't, you can ask for resources from us. There's some changes to the way what CESM3 might do and how resources will be allocated. So we might have opportunities for contributing to different sorts of community experiments. So we'll probably seek feedback for that. But otherwise, yeah, we'll send out emails and we'll have a winter working group meeting. But thank you for coming. We have a break, and then it's the afternoon session to celebrate the history of CESM3, and there will be the chief scientist there, so our very own Marika will be on the chief scientist roundtable discussion thing. Thank you.